We'll prove two proofs that are important to linear algebra. The first is the classic Nullity Theorem, which reads as follows. If T from V to W is a linear transformation between two finite dimensional vector spaces over a field F, then T induces an isomorphism T star from the kernel, from V quotiented against the kernel of T, which makes it isomorphic to T of V, where T of V is the image of V under T and is a subspace of W, is a subset of W, such that the dimension of V is equal to the dimension of the kernel of T plus the dimension of T of V. In particular, T itself is an isomorphism if and only if the kernel of T is equal to 0 vector and T of V is equal to W. Also note that with this proof we show that, we've already shown that T of V is as an image is precisely as a subset is also a subspace. That way we can take its dimension. Another note is that this object, the dimension of a kernel of some linear transformation, is sometimes called the nullity of that linear transformation, and the dimension of the image of a transformation is sometimes called its rank. The rank, in particular the rank definition, is related to some of the matrix operations you perform with it, and therefore that's how we get the name, the rank nullity theorem. With that, let's begin the proof. Let's let V naught be the kernel of T. Then we know that V naught is a linear subspace of V. Since we have a linear subspace, we know how to take quotient spaces of vector spaces. That means we can construct the quotient vector space V divided by V naught, and these are the subsets V plus V naught, which is a subspace of V. And since we'll note that T of V naught is equal to 0 vector, the linear transformation T maps each of these subsets to the same element. That is, T of V plus V naught is equal to T of V plus T of V naught, and T of V naught we know is a 0 vector, and anything plus a 0 vector is just that thing itself, so that'll give us T of V vector in W. That is, every element of this form, no matter what V naught you put on the right side, is sent to the same element T of V within W. This association, where we simply take T of V plus V naught, is what determines the mapping T star, because T star has to act on elements of V over V naught, so the elements of V over V naught are this, and then the function we actually apply is T itself. This is what determines the mapping T star from V naught to V naught over V to W. And we can check this as a linear transformation, having as its image the linear subspace T of V within W. That is, since V's are not in the kernel, they are sent to non-zero vectors, therefore they make up the image. And finally, we note that simply putting the 0 vector, which is an element of V, will get sent to the 0 element of W, and therefore you have the image being a linear subspace. And you can check closure and scalar multiplication as we had before. Next, we'll note that an element V plus V naught within the quotient space is in the kernel of the linear transformation T star, if and only if T of V plus V naught is equal to T of V is equal to 0 vector, which is the condition that V is in V naught. Hence, V plus V naught is equal to V naught is the 0 vector in this quotient space. That is, if you take any element of the kernel and you add it to some element of the kernel, that's going to end up being sent to 0. And we consider this as the 0 vector in this because it gets sent to 0. And we'll also note that we can also consider it as the 0 vector because any element of V naught plus any element in the quotient space will still be that element in the quotient space, since the element of the quotient space only cares about the part that is not inside the kernel. But this shows that our linear transformation is an isomorphism. And to recall, let's go back to 1.47, which is our definition of T star, because we've shown that, as we recall, the previous lemma is that a thing is injective if and only if its kernel is the 0 vector. And we see that the kernel of T star is any V naught, which is the 0 vector in the quotient space. Therefore, we have an isomorphism. And then once we can get 1.48 following from theorem 1.8, which was a precursor to the rank nullity theorem, which says that the sum of the dimensions of a space quotiented against the subspace plus the dimension of the space of the subspace itself is the dimension of the original space. In this case, the space quotiented is V over V naught, but we've shown that we have an isomorphism between V over V naught and W. Therefore, since we have an isomorphism between v over v naught and w, then we have, between v over v naught and the image of t, since we have isomorphism between those two, then they have the same dimension. Therefore, in our previous, in theorem 1.8, we can substitute in, instead of the dimension of v over v naught, we can substitute in the dimension of the image of v, i.e. this linear subspace. And that's how we get this term. That is, instead of the dimension of t of v, we can substitute in the dimension of v quotient v naught, which we know has the same dimension since we have an isomorphism t star. And then we apply theorem 1.8 to get this, where we have that v naught is the kernel of t, is the subspace of interest from theorem 1.8. And then finally, we will note that it's clear that t itself is an isomorphism, if and only if the kernel of t is equal to 0 vector. This is because if the kernel of t is a 0 vector and t of v is equal to w, then t is an isomorphism because it's a, it has a 0 kernel and it covers the entire space w. Therefore, it's an isomorphism. Fantastic. That's our proof of the rank nullity theorem using two lemmas that we've just proven in previous videos. The explicit descriptions of linear transformations and the determination of their properties for mappings between finite dimensional spaces rests on their effect on the basis of the vector spaces, as we will see in this following theorem, the mapping theorem. Before we start that, a kind of description of this comment is that to consider what a mapping does on a whole space, it suffices to consider what it does on the basis elements of that space. Since basis elements, you can form any element in the space by linear combinations, and since t is linear, you can simply go back to find what t does on the basis elements to see what it does on any arbitrary element, so you can see what it does on the whole space. So let's prove some facts about this. Theorem 1.11 is the mapping theorem, which says let v1 to vn be a basis of vector space v, and w1 to wn be a basis for vector space w, and they're both over field, or each of them are over their own respective fields. And we say any linear transformation t from v to w is determined fully by the images t of vi of the basis vectors, and a linear transformation t from v to w can be defined by specifying as the images t of vj any arbitrary n vectors in w. Next, we're going to show that the linear transformation defined by the values t of vi is injective if and only if the vectors vi are linearly independent. And then we'll show that the linear transformation defined by the values t of vi is surjective if and only if the vectors of t of vi span all of w. And finally, we show that two vector spaces over field f are isomorphic if and only if they have the same dimension. That's a lot of things to prove, so we're going to prove it in parts. So for the first one is kind of what the comment was saying, which is as follows. If t from v to w is a linear transformation, then t of a linear combination is equal to a linear combination of these images t of vj by noting that t is linear, so we can pull it through the sum and pull out the scalar factors. Hence, the full linear transformation, i.e. what t does on any arbitrary element, note that since v is a basis, this linear combination represents any arbitrary element of the vector space v. And what it does on each of those elements is fully determined by what these t of vi look like, i.e. we just add and use the scalars from before on each of these t of vi's. And we'll note that for any specified vectors t of vi within w, the linear transformation is a linear, defined by this, is a linear transformation taking these values. That is, choose any vectors in the image. We can figure out what they are by decomposing them into this linear combination and then figuring out what their pre-image is by figuring out what vj's are. Next, let's have 2. The linear transformation t determined by the images t of vi fails to be injective if and only if there are scalars aj within f, not all of which are 0, for which this is true. That is, since vj is a basis, to show this not injective, we need to show that if we have unequal elements, then they always have unequal outputs. But we're going to suppose that, but if they have equal outputs, then we can write the equal outputs as some aj's summed on all of these. And then we can subtract them over and get 0 vector on the far side, and then the one linear combination minus the other on the other side. And then we simply let each of the AJs be the difference in the coefficients of each of the quote-unquote image vectors, and then we can form this thing. However, this is precisely the condition that the vectors t of vj are linearly independent, because we want a sum, a linear combination of the image vectors equals to 0. That is, it fails if there are non-zero scalars for which this is true, but if there are non-zero scalars for which this is true, that means t of vj are linearly dependent. Therefore, it fails if and only if there are scalars such that this. And you can check the reverse direction as well. It's quite easy. For 3, we will note that since the linear transformation t is determined by the images is given by 1.49, recall that that's this sum here, or simply applying the linearity of t. It's clear that the linear transformation is surjective if and only if the set of vectors t of vj span w. That is, to show that it's surjective, that means this sum is an arbitrary element in the output space. To show that output space covers all of w, you need to show that any w can be written as a linear can be written in this form. But saying that this can be written in this form means that there exists a linear combination. There exists some sum and some coefficients such that that sum and linear and those coefficients give you that vector w. But if that were true, then we'd have that t of vj is a basis for, since a basis is the smallest spanning set that is linearly independent, and we've shown the linear independence condition. I'm sorry, we just need to show the spanning. We don't even need the linear independent condition. We just need to show that if it's surjective, then these sets span all of w. And finally, for 4, we will note that if t from v to w is an isomorphism, it must be both injective and surjective when viewed as a mapping. That is, it must be a bijection, and it preserves the structure. It then follows from the preceding parts of this theorem that the vectors t of vi are a basis for w, and consequently the dimension of w is equal to the dimension of v. That is, we've proven that if it's an isomorphism, then it's both injective and surjective. Therefore, t of vi must span and be linearly independent. Therefore, they serve as a basis for w. And therefore, since any two bases have the same number of elements, i.e. the same dimension, we have the dimension of w is equal to the dimension of v. On the other hand, if the dimension of v is equal to the dimension of w is equal to n, and v1 to vn is a basis for v, while w1 to wn is a basis for w, by the preceding part of this theorem, i.e. the earlier sections, there's a linear transformation t from v to w, sending vi to wi, and this will be both injective and surjective. So it's an isomorphism, which will suffice for proof. So to prove that last big line, we let t be the map sending vi to wi. This is going to be injective because we can apply the linearity and we get that the output vectors, there is no possible way of having the output vectors overlap each other since wi are linearly independent and vi gets sent to wi. And we see that it spans because wi is a basis, therefore a linear combination of basis elements will cover every element in the space since it's a basis, so it's surjective. And then to show that there is a linear transformation, we simply recall that we simply recall the second part of 1, that is, we specify the images of anything and of any arbitrary n vectors in w, and we get a linear transformation. Therefore, we've shown that there is a injective and surjective linear transformation. Therefore, it's an isomorphism, and since it's isomorphism, then the dimension. Since it's isomorphism, we're done because we assumed that they have the same dimension to start with. So we've shown that if it's a dimension, then there's an isomorphism, and if they're isomorphic, then they have the same dimension. With that, we've proven our theorem. I've proven 2 big theorems, so it's important to try to go through all of these steps to review. With that, thank you for watching.